Hello friend, welcome to my YouTube channel Electrical Boost. Today we are going to discuss how to find Norton equivalent circuit if dependent sources are present. Okay, in our previous video we learned about if only only independent sources are present, how to deal Norton equivalent circuit. Okay, but in this case both dependent and independent source are present, dependent and independent source are present. Then how to find Norton equivalent circuit? Let's start. Here the question is given that find Norton equivalent circuit across AB. Okay, here the question is given that find Norton equivalent circuit across AB. Okay, for draw a Norton equivalent circuit we need two components. First one is Norton current, that is IN is called Norton current, or you can say that short circuit or short circuit current. Okay, and another element is needed, that is Norton equivalent resistance. Norton equivalent, that is RN. Norton equivalent resistance. Okay, for finding IN we need to short circuit this branch, or where to find Norton equivalent circuit. Here we need to find Norton equivalent circuit in across AB, so that we need to short circuit this AB. We redraw the circuit likewise. See, this is as usual 15 volt, and this is okay, this is 6 ohm, and this is 2 ohm. Okay, this is dependent source. Okay, this is a resistor. Okay, this is a resistor. Okay, and we short circuit this AB, branch, and we need to find here IN. Okay, this is 10 ohm. Okay, and this is 0.5 Vx. Okay, this is 2 ohm. Okay, this is plus or minus Vx. Okay, this is 6 ohm, and this is 3 ohm. This is 50 volt. Okay, here you see, if we short circuit this branch, this 10 ohm directly eliminate, because there is no current flowing to this branch. If no current flowing to this branch, then this branch is nearly equal to deactivated. Okay, so here the dependent source is a voltage control current source. Okay, this current source depend upon this voltage. Okay, we need to find this current. We know that this current is equal to this much current plus this much current. Okay, this current is equal to this much current and this current. This carefully was, this IN is equal to, let this current is I1. Okay, let this is 0.5 Vx. Okay, this is the mix of IN is equal to, here IN is equal to I1 plus 0.5 Vx. Okay, this is the current of IN. Okay, we need to find this I1 value and this Vx value, so that we can find this IN. Okay, so for finding I1 we need to see this I1 current is totally flowing through this one, so here only single node is present. If we apply KCL at this node, we can find I1. Okay, because this current, this is the, okay, here this current, this I1 equal to mixing of this current and this, okay, sorry, this branch and eliminating this branch. Okay, this is the scenario. Okay, let here we can apply, here we can apply nodal analysis. Okay, if you take node, this is node voltage, let this is node voltage Vx, let this is the node voltage Vx. Okay, let this is the node voltage Vx. We can apply node equation. You can see that this node equation at node equation node. Okay, this is for finding I1. Let the node equation is equal to how much? This is let this is Vx, because this branch current, this branch voltage is Vx, so that we can take node voltage Vx. Okay, this Vx minus Vs minus 50 divided by 3, then plus Vx minus 0 by 6, this is by 6, then plus Vx minus 2, sorry, Vx minus 0, because this is totally 0 potential, this is totally 0 point because the short circuit, so that Vx minus 0 divided by 2 is equal to 0. This is the node equation at this node. Okay, let we find, take it LCM. The LCM is, let we take the LCM is, we can take 6. Okay, let take LCM is 6. Okay, let take it 6, LCM is 6, so that it is 2 Vx minus 100. Okay, minus 100 plus Vx minus, sorry, minus, it minus not plus. Okay, plus this is 3 Vx is equal to 0. Okay, you find the Vx value, this is 2 Vx, let 6 in this side, so that 2 Vx minus this is total, sorry, this is total 2 5 6 Vx minus 100 is equal to 0, so that the Vx is equal to 100, sorry, 6 Vx equal to 100, then this Vx is equal to 100 by 6. This is hello, this is 16.667 volt. Okay, when we find Vx, okay, we need to find this I1. This I1 is equal to Vx by 2. Okay, this I1 is equal to Vx by, this I1 is equal to Vx by 2, so that this I1 equal to 16.667 divided by 2, this is equal to 8.33 volt, sorry, ampere, 8.33 ampere. Okay, finally we need to find this IN. We know this IN is equal to this much current and this amount current. We know this voltage, so that we can find this value of dependent source. Okay, value of dependent source, and I find the I1, so that this is the sum of the this and this. Okay, so that this IN is equal to this 8.33, this is I1 value. Okay, plus 0.5 into Vx equal to 16.667. okay, this is finally 16.667 ampere. Okay, this is a final IN. Our next to find the value of Rn. Okay, then we're going to for finding Rn. Okay, see, for finding Rn, for finding Rn, okay. In our previous in a previous video where only independent sources present, for finding the Norton equivalent resistance is one method or easiest method, but in this case where the dependent sources are present, we cannot deactive or dead the dependent source, because if we deactive this source, that means we need to change the value of 6 ohm. When the value of 6 ohm change, then it will be changed, okay. So that we cannot affect the dependent source in any theorem, okay, okay. So that we need to a different approach, okay. We know that this Rn is equal to open circuit voltage divided by short circuit current, okay. We already find this short circuit current, we need to find this open circuit voltage, okay. For finding the open circuit voltage, we need to open this AB terminal. In our question already it open, so that no difficult to find. It is the one of the method, and there is another method to finding the Rn, where you use a source or dummy source, okay, where we discuss this topic we discuss in Thevenin's theorem problem, okay. You can see in I button, okay. So you going to this method, okay. Again redraw the questions, okay. This is the questions, okay. This is the question, this is 15 volt, okay. We need to redraw, okay. Sorry, this is the dependent source, this is AB, where need to find this VOC, okay. And this is 10 ohm, okay. This is 0.5 Vx, okay. This is 2 ohm, okay. This is 6 ohm plus or minus Vx, okay. This is 3 ohm, okay. This is 50 volt, okay. We need to find this voltage. If you need to find this voltage, we need to apply here I am going to apply two node equation. Here is the one node and here is the another node, so that we can find this open circuit voltage, okay. Here let this is node 1, okay. Let this is the node Vx, because this potential is Vx. Here the node voltage is VOC, because we take it as finally VOC, okay. So that we first apply node at Vx, node at Vx, okay, at Vx, okay, at Vx, node at Vx, so that we put the equation, okay. First we read the current are leave from the node, so that we draw this is Vx minus 50 divided by 3 ohm, then plus Vx minus 0 divided by 6, then plus this is Vx minus VOC divided by 2, okay. This is our first is equal to 0. This is first equation. If we modify this equation, this is 6, and this is 2Vx minus 100, 2Vx minus 100 plus Vx plus 3Vx minus 3 VOC is equal to 0. Okay, again this modify equation is 2vx plus 3, this is 6vx minus 3voc is equal to 100. This is our first equation. Then the node equation at VOC. Okay, node equation at VOC. This is VOC means this is here. Okay, so that current is entering here, the node, total node, this one. Okay, current is entering but other current is leave, so that this VOC minus Vx by 2 plus VOC minus 0 divided by 10, then minus 0.5 Vx is equal to 0. Okay, let's take it LCM. This is 10, this is 5 VOC minus 5 Vx plus VOC we take here, this is 0.5 Vx. Okay, then go to there. Okay, here the question is finally solve the equation is, this is 6 VOC minus 5 Vx equal to this is 5 Vx. Okay, then this final equation is likewise 6 minus 10 Vx plus 6 VOC is equal to 0. This is our second equation. This is our second equation. Okay, this is our second equation. Okay, if we by solving equation 1 and 2 we get only we need this VOC, so that VOC is equal to 166.667. okay, 166.667 volt. Okay, this is our open circuit voltage. We need to find this node voltage is also known as open circuit voltage. For finding Rn, we know that this VOC divided by ISC. We already find ISC in this. Okay, we already find the ISC, so put ISC means IN means ISC. Okay, this is 160.667. okay, this is 16.667. this is approximately, this is 9.999 is equal to approximately equal to 10 ohm. Okay, we finally got this Rn and IN. Okay, IN. So we finally got IN, Rn. Okay, so that we draw Norton equivalent, final Norton equivalent circuit. Is Norton current parallel with Norton resistance and open circuit AB. Okay, this is 10 ohm. Okay, this is 16.66 ampere. Okay, finally we got the answer. Thank you for watching this video. Please like and subscribe my channel. If you any doubt, please comment. Thank you.